Hello class, today we are jumping into the ideal gas law and Dalton's law of partial pressures. We're also going to do a little bit of gas stoichiometry, so get used to doing some mole conversions again, and we'll go from there. This still goes well with the quest on gases, and also might help you on some of the gas law free response questions. So the ideal gas law. Ideal gas law is PV equals nRT. Here the units are very, very specific. With the simple gas laws, we didn't care about the units as much, with the exception of temperature. Temperature always has to be in Kelvin. With the ideal gas law, all of the units are going to be dependent on your gas constant. Typically, your R value will depend on, the units for your R value will depend on P and V. So whether or not your pressure and volume are in different units. But the standard is to use atmospheres for your pressure. The most common gas constant we'll see in a little bit. We're always using atmospheres. We're always using liters for volume. Temperature is always in Kelvin, and then we always use moles. So N is for moles here. We also know there's an application to this. You might have seen this way back in the summer work, or in that first unit when we were dealing with empirical formula. If we're given the mass of a sample, we can use the ideal gas law to determine the molar mass of the gas. So for instance, if we have the ideal gas law, we can first solve for moles. And then we can treat the unit for molar mass. We know the unit for molar mass is grams per mole. We can treat that like an equation. Typically, they'll give you some sort of sample mass. So they'll give you volume, pressure, temperature, and they'll say you've got like 5 grams of this sample. And we're like, okay, cool. So then you take that, you plug it in, you solve for moles, then you take that 5 grams of your sample and then divide it by the number of moles you get from the gas law, and you get your molar mass. There are some examples you might see on the quest that are like that, so just keep an eye out for it. We also have an application of the ideal gas law that uses density. I know that this play posit is going to run a little long, so I actually moved that example using density to the last play posit, so keep an eye out for it there. We know that the molar mass is equal to the density times R times T over P. Density has, we know the definition of density is mass over volume. In particular, we're using units of grams per liter in all of these problems. I know you're so used to looking at water and thinking, oh, the density of water is 1 gram per ml. And while that's true, we have to remember that when we're using this equation, we have to do grams per liter because of the units of R. My volume is usually always in liters, okay? So you can use that to find the molar mass as well. So there's 2 different ways we can find molar mass. If you know the density, you can find the molar mass that way, or you can use the method described here if you don't have the density. Both ways work, okay? Oh, wrong direction. The other thing, molar volume. We can find our gas constant by using the volume of 1 mole of gas at STP, which is standard temperature and pressure. Remember that STP, your standard temperature is 0 degrees Celsius or 273 K, and standard pressure is 1 atmosphere. We also know that at STP, the volume of 1 mole of gas is equal to 22.4 liters. Now, that is one of the things you try to prove in your in one of the labs that we do here in AP, so keep an eye out for that. If you wanted to solve for R, we could rearrange everything here. We end up getting PV equals NT, or PV over NT, right? If we divide both sides by NT, that cancels out. We get R is equal to PV over NT, and that's exactly how we're going to solve and find our gas constants. So let's go ahead and do it. We're going to use our standard conditions. We know that we have 1 atmosphere, that's our standard pressure. We've got 22.4 liters, that's our molar volume. And we've got 273 Kelvin, 1 atmosphere, oh, I said 1 atmosphere already, and then 1 mole, okay? So then when I go ahead and plug those into the calculator. Oop. Sorry. 1 atmosphere times 22.4. If I could actually push in all the correct characters here. And if I divide that times 1 mole times 273, technically 0.15 Kelvin, we get 0.082006. 0.082006, otherwise known as 0.0821, 0.0821. And we know that those units don't cancel out, so we got ATM, liter, mole, and Kelvin. So if you've ever wondered where those units come from before, that's where they come from. ATM, liters, mole, Kelvin. It's one giant unit. Okay? And it comes from the fact that we arranged the gas law. We rearranged the gas law to be pressure times volume over moles times temperature. And those are the respective units for each. When we're looking at the ideal gas law, the other thing that's really important is that we can use the ideal gas law to calculate any of the problems, even the ones with the simple gas law relationships. We just assume that those things are held constant. So I'll show you an example in a minute. But first, let's do a simple ideal gas law calculation. We know that PV equals nRT. Here we have a sample of hydrogen gas, and our volume is 8.56 liters. We also know our pressure is 1 atmosphere. And our temperature is 0 degrees Celsius. We want to know our moles. All right, 0.0821 atmosphere, liter, mole, Kelvin. And my temperature, remember to convert to Kelvin, 273. Okay. When I go through and solve here, I get N is equal to PV over RT. So I'm going to actually just plug that in the calculator that way. I'm not going to waste time rewriting it. I've got 1.5 times 8.56, and then I'm going to divide it by 0.0821 times 273. And I get a volume of 0.57, I got 2 sig figs, so 0.57 liters, okay? I know my unit is in liters because atmospheres cancel. Liters also cancels here. Oh, I'm sorry. I put the wrong unit on this thing. I'm glad I'm checking. I was solving for moles. This is moles. 0.57 moles. Right? Liters cancel, Kelvin cancels, and I'm left in moles, so my answer should be in moles. See? Always check your units, so that way you can get the right answer. Okay? Here's a good one. Getting into some of the gas stoich. A sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles are present? Well, you might be sitting here scratching your head. There are a couple of different ways we can do this. We know that my standard temperature is going to be 273 K. My standard pressure is going to be 1 atmosphere. I know my volume is 1.75 liters. And I could solve for moles, but that's a lot of work. I could sit there and plug in and figure out how many moles are present using the ideal gas law, or I can remember one key thing at STP. I know that 1 mole is equal to 22.4 liters at STP. I can figure out how many moles there are. If I've got 1.75 liters, you can probably guess that we're using this as a conversion by now. 1 mole of a gas is 22.4 liters, so I certainly have less than a mole because my volume is smaller than 22.4 liters. But if I go through and check, those are going to cancel out, and I will get my moles of gas. 22.4 liters. All right, so I end up getting 0.078, let's do 3 sig figs, 781 moles of gas. Very small amount. You put it in scientific notation, they said 7.81 times 10 to the negative second. So that's fine. We have this many moles of N2. It's a little shortcut. Don't overestimate the power of that. Again, it has to be at STP. Okay. All right, Dalton's Law of partial pressures here. Dalton's Law of partial pressures states that basically the sum of the pressures of the individual gases in a container can add up to equal the total pressure. So obviously, if you have only one type of gas in your container, that gas is contributing to the total pressure that you're getting. If you've got multiple gases in your container, the sum of those pressures give you your total pressure. There is actually a derivation for this that comes from the ideal gas law. We know that there's also a relationship between the moles here. Since we know ideal gas law has a mole relationship, we can start looking at the mole fraction, which is the moles of a particular gas over the total moles in a container. And because of the ideal gas law, we can look at that relationship and derive and figure out that the pressure of a gas is equal to the mole fraction, which is chi. That's the Greek letter chi. I know it looks like an X. The mole fraction chi times the total pressure gives me the pressure of my individual gas. So there's really a couple of applications here for Dalton's Law. We're going to explore a few. So it says mixtures of helium and oxygen are used in scuba diving tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees in 1 atmosphere and 12 liters of oxygen at the same temperature and pressure were pumped into a tank with a volume of 5 liters. They want to calculate the partial pressure of each gas and the total pressure in the tank. Okay, so in order to calculate the partial pressure of the gas, we first need to know how many moles of gas there are. So we can set this up. Our ideal gas law, we know the moles of He is going to be equal to our pressure, 1 atmosphere, times our volume, 46 liters. We've got R is 0.0821, and we've got our temperature, which is in Kelvin, 298 K. All right, so 46 divided by 0.0821 times 298. I know I'm going to have 1.88 moles of helium. Okay. And with 1.8 moles of helium, I also need to know the moles of O2. Because if I know the moles, I can figure out their contribution to the total pressure. I will show you how. But if I know the moles of each, I can then put that into the new gas law situation and figure out my pressures. Okay, so same deal, 1 atmosphere, but this time it's 12 liters, 0.0821, and 298 K. Okay, so 12 divided by 0.0821 times 298. Okay, so initially, before I put them in, I've got 0.49 moles of O2 and 1.88 moles of helium. Then I put them in the container. I know my container now has a volume of 5 liters, so things are going to spread out. I need to figure out my pressure inside the new container. So the pressure of He is going to be equal to our nRT over V, which is our volume, right? This time if we're going over pressure, nRT over V. Yep. So I've got 1.88 moles of helium times 0.0821 times 298 K. Thankfully, they're still at the same temperatures. And then I've got 5 liters. All right. So 1.88 times 0.0821 times 298, and divide this by 5. All right, I get I guess I technically have 2 sig figs here, so I've got 9.2 atmospheres of pressure from helium. So this is my partial pressure of helium. And if I go through, do that same calculation, but this time change my moles for oxygen. All right, and then the moles of oxygen is 2.397. I guess I could say 2.4. Right, 2.4 atmospheres for oxygen. I've successfully found my partial pressures, and then to figure out my total pressure, I just have to add them together. I know that my P total equals the P of O2 plus the P of HE, and when I add these things together, that's 9.2, I get 11.6 atmospheres as my total pressure. Okay. So a couple things. First, find the mole fraction. Once you have the mole fraction for your initial, not mole fraction, but once you have the moles for your initial condition, then you can plug that into the gas law under the new condition, which is my container of 5 liters. And then you get the pressures of each and then add them together. Sheesh, that was a long problem, but it was a good one. All right, this one is a little easier. Partial pressure of oxygen was observed to be 156 torr in air with a total atmospheric pressure of 743 torr. Calculate the mole fraction. All right, mole fraction of O2. Again, moles of O2 over moles total. Well, if you think about it, if we're multiplying that times the pressure total to get our pressure for oxygen, right? If we think about our equation for a minute, P of O2 is equal to our mole fraction times the pressure total. If we know our pressure of O2 is 156, and we know that our total pressure here is 743, then I don't actually need to solve for the moles at all. I can just rearrange and get 156 torr over 743 torr and get my mole fraction. Notice that a mole fraction doesn't have any units. That's okay. Think about what a fraction is. In this case, it's basically a percentage. All right, 0.21 would be my mole fraction. So about 21% of that air is oxygen in this situation. All right, here is a good gas stoic question, but it also gets into partial pressure, which is really good. It's a good lab question because there's a couple things we have to consider. We have to consider the pressure of our oxygen, and we also have to consider the vapor pressure. So if you're not familiar with the idea of vapor pressure, we'll cover it in a couple of units from now when we're talking about solutions. Vapor pressure, essentially the idea with vapor pressure, we know that when we have a liquid, such as water, those particles on the surface of the water are evaporating, right? We know that it takes quite a lot of energy for us to boil, but if we leave a glass out over time, some of those particles do transition to the gas state, and it's because of their vapor pressure, essentially the amount of pressure contributed by the particles on the surface transitioning to a gas. So we have to account for vapor pressure here. So it says a sample of solid potassium chlorate was heated in a test tube and it decomposed, gave us that reaction. That's where the stoic part's going to come in. It says that the oxygen produced was collected by displacement of water at 22 degrees Celsius at a total pressure of 754 torr. The volume of gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees Celsius is 21 torr. Calculate the partial pressure of oxygen in the gas collected, and then also calculate the mass of potassium chlorate in the sample that was decomposed. So the good news is vapor pressure is the easiest part, okay? Not vapor pressure, partial pressure. So we know that our pressure total is going to be equal to the pressure of oxygen plus the pressure of water when we're talking vapor pressure. We're given our pressure, total pressure at 754. All right, 754 torr. If we subtract out our vapor pressure of water, we get our pressure for our oxygen gas. Okay, I'm just moving it here because I'm being conscientious of space. And it would help if I could write. What is wrong with this pen? All right, 21 torr. All right, and we do the math. Our partial pressure is 733 torr. Okay, so now here's where it's tricky. We need to figure out the mass of potassium chlorate. This is where the gas stoich comes in. Well, if I'm looking for the mass of this, I don't know anything about this. The only other thing I can possibly use to get the mass of that is figuring out the mass of oxygen. If I have my mass of oxygen or even the moles of oxygen, I would be in good shape. Well, the nice thing is I have my partial pressure. I know I can take my partial pressure of 733 torr and I can plug that into the ideal gas law. And when I plug that into the ideal gas law, I can get my moles of oxygen. So first I need to convert it and figure out my pressure in atmospheres. I'm just going to plug it straight into my setup here. So 733 divided by 760, 0.964 atmospheres. And I'm solving for moles here, so I want PV over RT. All right, I'm told that the volume of gas collected is 0.650 liters, which is a ton of gas. All right, I know R is 0.0821, and I know my temperature is 22 degrees Celsius, which is 295 K. All right, so I can go through here. This times 0.650 divided by 0.0821 times 295. And I now have my moles of oxygen, 0.0259 moles of oxygen, moles of O2. Now that I have my moles of O2, this becomes a stoichiometry problem. I need my mole ratio. So 0.0259 moles of O2. If I want moles of O2 to cancel, I've got to use my coefficients here. I've got 3 moles of O2 for every 2 moles of potassium chlorate. All right, and now that I'm in moles of potassium chlorate, I know 1 mole of potassium chlorate is equal to its molar mass. So you're going to need to figure out its molar mass. 16 times 3 plus 35.45 for chlorine plus 39.9. I'm doing this off the top of my head. 39.9 for potassium. I believe that's correct. Or is it 39.19? Either way. If I'm wrong, you can double check me on it. So 123.35 grams. If I have my molar mass wrong, I apologize. I should have pulled up a periodic table. But that's okay. Moles of O2 cancels. Moles of potassium chlorate cancels, and it'll be left in grams. I've got my 0.0259 times the top, which was 2, divided by 3, which is the bottom, and then times the top of the next one, 123.35. All right, and I've got 2.12 grams, actually 2.13 grams, actually, sorry. Looking at my sig figs, 2.13 grams is my mass made. Okay. And that is all for today.